Hi all, welcome back. And in this video, I want to talk about two properties of transformations. So if you recall, when we were talking about transformations, the particular kind we're interested in is linear, but in fact, these two properties are going to apply to all transformations. But before we get into that, I just want to recall the picture that we drew on the board in class. So if we had, let me get out of the multicolored writing. So if I have a transformation T from Rn to Rm, I can draw the following picture. So the input is going to be all vectors in Rn. In particular, I can have some vector x, and I can apply my transformation to x. So if I apply t, then what I get is some new vector, let's say t of x. And this lives over here in, so not necessarily Rm, but some subset of Rm. So maybe it's everything, but maybe there are some vectors that are left out where I could have something out here where maybe there is not a vector in Rn that gets sent to this vector. So let's call this one maybe u. So maybe there's no x such that t of x equals u. All right. And so what I want to do, so we have all of this in mind, and I want to talk about two properties. And the first property is what's known as 1 to 1, often abbreviated just with the symbol 1 to 1. And I'm going to say that a mapping or a transformation, same thing, not necessarily linear, just any transformation from, or actually let me just write t, call it t, from Rn to Rm is said to be 1 to 1 if each vector b in Rm is the image of at most one x in Rn. So going back up here, I have my vector x that's in Rn, and it's being sent somewhere over here in Rm. And what this says is if I take any vector, let's say b in Rm, so b could be here, or b could be out here. So maybe I'll call this b1 and b2. And what this is saying is that my vector b is the image of at most one x, which could mean this. So maybe I'll make this blue. So this right here would mean that b2 is not the image of any vector in Rn. That's fine. And this b1 here, a different color, let's say green. This one can be the image of at most one vector in Rn. So maybe I'll say vector y can go over here. But what I could not have is another vector let's say v, also going to the same vector b. So this would mean that I have two vectors going to the same thing, and that can't happen. And that leads to, so there are a couple different ways to define one-to-one, and so another rephrasing of this is the following. Another way. And what I can say is that if t is one-to-one, then for each b in Rm, the equation t of x equals b, has either one unique solution or no solutions. And so this green up here was sort of representing the one unique solution. So only this vector goes to b, and that's fine. But again, I cannot have this second vector going to b. Okay, and this b2 on the outside over here is representing the situation where I have no solutions. So this is fine as well. All right. And there's a third way to think about this, and it comes from maybe this motivation of how would I actually go about proving that a transformation is one-to-one. And so what I'm going to say is that if I have two vectors, let's say x and y, and let's say they do both go to the same thing. So maybe here, let me draw, let's see, x, and let's say both x and y go to b. Okay, well, if the transformation is one-to-one, we know that can't happen. I can't have them both going there. And the only way that this would be possible would be if, in fact, x were to equal y. So if x equaled y and they both went to b, then that would be completely fine. Okay, and so that leads to this third way. Let's say yet another way. And we'll say that if t is one-to-one and t of x equals t of y, this implies then that x must equal y. And let me circle this in blue for the reason that this right here is what we're going to use in the future to argue that a transformation is one-to-one. Okay, so we'll do two examples. The first is going to be a non-example, so an example of a transformation that's not one-to-one, and then we'll look at an example that is one-to-one. And so before I do the example of the transformation that's not one-to-one, I want you to pause the video and see if you can think about what property this transformation has that I'm going to highlight in order to argue that it's not one-to-one. Okay, so here is the non-example. So let t from R3 to R2 be the transformation given by t of a three-dimensional vector, let's say ABC, is equal to a plus b plus c and a plus 2b plus 3c. And I'm going to say this is not 1-to-1 because, and hopefully this is what you arrived at too for what we need to see, and it's that t of two different vectors, in this case we can use the 0 vector, and this other one, 1 minus 2, 1, t applied to both of these vectors is the same thing, and in fact it's 0, 0. And so that would be this example here where I have an x and I have a y and they're both going to the same thing. So I can think of this as my x and this as my y. And so we'll say here t of x equals t of y, and x does not equal y, and that implies t is not 1-to-1. Okay, so that's example 1. And here's example 2, an example of a transformation that is 1-to-1. So here, let t, this time from R2 to R2, be given by here, t of a b is going to equal 2a plus 3b and 3a plus 2b. And if I want to argue that this is not, or that this is 1-to-1, maybe pause the video and think about how I would do something like that. But okay, and the way to do this is to show that if two arbitrary vectors x and y have the same image, then x must equal y. And so quickly we can do that by saying let x equal maybe a1, b1, and y equal a2, b2. And we'll suppose t of x equals t y, whatever that is. And then I'm going to show that this implies x must in fact be the same as y. And so t of x, we know just by plugging a1, b1 into our formula for t. So this on the left is equal to 2a1 plus 3b1, and then 3a1 plus 2b1. And I'll do the same thing for y. So here I get 2a2 plus 3b2 and 3a2 plus 2b2. And if the first part of this is true, then what that means is that this and this must both be equal. So this then implies, that implies this, and it implies the following system of equations: 2a1 plus 3b1 equals 2a2 plus 3b2, and 3a1 plus 2b1 equals 3a2 plus 2b2. And even though we have 4 variables here, we can think of this as a system. We can combine, we can add, we can subtract, and I'll let you do that on your own time if you'd like, but what ends up happening here is that this implies A1 equals A2 and B1 equals B2, which then implies that x must be equal to y, and so t is 1 to 1. Okay, and lastly, let me say that there is a mathematical word for 1 to 1 as well. So oftentimes you'll hear mathematicians use the word injective. Use the word injective to mean 1 to 1. And all that is just a fancy word for this definition that we know. All right, and now the second property that I want to talk about is what's called one-to-one, or sorry, what's called onto. And we'll say that a mapping or transformation, again, not necessarily linear, is said to be onto if T from Rn to Rm has the property that for each B in Rm, there is at least one x such that T of x is equal to B. Okay, so let's go back up and look at our picture. And what that means is that here, okay, there we go. Yeah, what that means is that I can't have these vectors sitting alone on the outside. So all possible vectors in Rm are located inside this range of my transformation. So in fact here, this range isn't a subset of Rm, it is actually equal to Rm. But the other thing that I want to point out that is okay is the following. So maybe I'll do yellow. So here for some vector, again, let's use B. It is fine to have two different vectors being sent to B. What I need is at least one, so having more than one is fine. Okay, and so let's do a quick example of what I mean by an onto transformation. Okay, example, and I'll say the transformation T from R2 to R2 given by T of AB. And actually here, maybe you could pause and think about on your own a transformation that you think would be onto. Okay, but one such example is the following, letting this just equal BA. And here I can say this is onto, can say, or we can show T is onto by showing that an arbitrary vector, let's say maybe, how about A1, B1 is the image of some vector in R2. And so if that's this is my vector here, then I just need to find a vector that when I apply t to it is sent there. And so here, that vector, say x, if I let this be equal to b1, a1, then t of x is equal to a1, b1. And so that means that t is onto, because for any vector you give me, I can find some vector that is sent there. And maybe just a quick example with actual numbers, I'll say if you give me the vector, let's say 3, 5, I know how to find a vector whose image is 3, 5. I know the vector 5, 3 has that as its image. Okay, and the last thing I'll say here is there's also a mathematical word for being onto, and that is surjective. So an onto transformation is also called surjective. That's a J. Okay. And one thing that I would also like to encourage you to do is to answer or think about questions along the lines of, can I have a function that is both one-to-one and onto? Can I have a function that is neither? Can I have a function that is onto but not one-to-one? And can I have a function that is one-to-one but not onto? So what are those functions or transformations? If they exist, what do they look like? And things like that. All right.